This is a demo of the performance of BFQ. I will show you what BFQ can do in terms of responsiveness, latency for soft real-time applications, and disk throughput. As for responsiveness, I will focus on the startup time of applications, but let's get it started. In the terminal with the largest window, I will show you the startup time of the same common application that I am using to control this demo, that is a terminal. In particular, the native terminal for this system is GNOME terminal. In the other two terminals, I will invoke commands to generate some background workload. In this terminal, you can see the current disk scheduler. In this moment, it is CFQ. From this terminal, I will invoke some commands to switch between schedulers, and finally, I will invoke possible other commands from this last terminal. There is also a monitor of the disk activity. This is a rotational disk with a peak rate around 95 megabytes per second. So, okay. To show you the startup time of GNOME terminal, I am using one of the benchmarks of the suite. It is a script that starts the desired application after dropping the page cache. So we get the worst case startup time of the application, and we put every scheduler in the same condition. This script for each invocation prints the measured startup time, especially it prints both the number of seconds and a bar made of sharps to show the time graphically. This script is showing now also the average startup time of GNOME terminal when the disk is idle. As you can see, the actual startup time, the sampled startup time, is close to the one with an idle disk, because now the disk is idle. It is actually lower, but variability is the norm with disk I/O. So we can start by adding the read of one large file. It's a sequential reader, and it is a greedy generator of workload, in that it generates its next disk request just after the previous one has been completed. As you can see, the throughput goes up, but also the startup time of GNOME terminal definitely up. Okay, we can go on and add also another typical task for a user, that is the copy of one file. In particular, this script copies one large file. Now the dangerous part of this demo starts, because the copy of one file generates a lot of write requests per second, and when this happens, the whole system or at least many applications may become unresponsive. The reason for that is the following. Writes are buffered until a certain ratio of dirty pages is reached, and from that point on, writes become blocking, dirty pages start to be flashed, and also serialization problems occur. To reduce the probability that the system becomes unresponsive, this copier is actually rate limited, but this just reduces the probability and does not eliminate the possibility that the entire system becomes unresponsive. As you can see, the startup time has gone up. Now it seems particularly long, and this is actually what I would like to show you. so I want to wait for this to terminate. In addition, we can also force the flash of all the pages, dirty pages, by issuing a sync. So we are waiting. Okay, if it does not terminate soon enough, I will stop it, because I think that, however, I have made my point about startup time with CFQ. Okay, let's stop it before we risk to lose even the control of the system. And okay, let's stop also this one, otherwise it does not. Okay, so to sum up, with CFQ and with this workload, we have that the startup time is on average probably 3 times the idle disk startup time. Maybe we can see it from here better here and here. And from time to time, the startup time just blows up. So you may say, okay, this is somehow normal because the system is under a heavy pressure because of the two generators, the two greedy generators of workload. But I will not be that sure. And now it's time to let BFQ come into play. So we restart the background workload and we switch to BFQ and repeat the same test. So iteratively start GNOME terminal. As you can see, now with BFQ, the startup time of GNOME terminal is the same as if the disk was idle. So you may say this is a lucky run because maybe dirty pages are not being flashed, so we can force the flashing of dirty pages by by issuing the sync command, by invoking the sync command. But again, apart some small fluctuations, the startup time is close to the one that we get when the disk is idle. Okay, we can now stop this workload and move to a heavier one. For example, let's try to mimic what could happen in an overload period. And to do that, we might start the copy of 3 files plus the sequential read of other 3 files. But as you can see, the startup time of GNOME terminal is still the lowest possible one, the lowest possible startup time. Let's switch to CFQ to see what happens. And again, everything slows down. And we had to wait. Okay, now let's stop even this. And just to show you the performance of BFQ, I want to raise the workload to an unrealistic level. 10 file read plus 10 file copies. And here is the result, as you can see. Now there should be more fluctuations, of course, because the workload is heavier, but the startup time is still definitely low and close to the one that we would get when the disk is idle. Okay, I think I've made my point about the performance of BFQ in terms of responsiveness. Now let's see what BFQ can do with a soft real-time application. Let's consider the playing of a movie. And as for the background workload, we can, for example, restart our 10 file readers. Okay, so with this background workload, we are going to start this movie and see what happens. On one side with BFQ, on the other side with CFQ. Okay, the movie is starting. And here we go. Okay, so as you can see, even if with this background workload, there is no glitch in the playback. Want to reduce the size of this window because to make things harder, I want to also restart the script that invokes the GNOME terminal and check what happens. Here we go. Now the movie becomes, this trailer becomes more demanding, but however the playback is still smooth, as if the disc was idle. I do like this movie. Okay, so let's stop it and let's switch to CFQ. Here we go. Of course, everything becomes slower. Let's restart everything from scratch. So we put both scheduler in the exact same condition. So first the background workload, then we start the movie and see what happens. Get ready for something bad, because as you probably have already understood, the player just does not start. Yeah, just to wait. Okay, this is the result with the CFQ. We may switch to BFQ just to see what happens. And here is the player starting again. We have already seen the quality of the playback. Okay, so this is all also for our test of the latency experienced by a soft real-time application. We can finish this demo by considering the throughput achieved by BFQ and comparing against the throughput achieved by CFQ. So here you can see on the disk monitor the throughput that BFQ is achieving. We are around probably on average, I think 85 or even 90 megabytes per second. So we are somehow close to the peak rate of this disk. If we switch to CFQ, we see instead, okay, now it has switched, an immediate decrease of the workload, of the rate of the disk, of the throughput of the disk. Here it is, in this part. To conclude, we may, for example, switch back to BFQ, and again the throughput, as you can see from the disk monitor, goes up and becomes close to the disk peak rate. And this ends this demo. Thank you for watching it.